Hi, this is Sholey Physics, doing an episode on the universal gravitation law. There's two scientists I'm going to feature in this one. Of course, if you think about gravity, you'll think about Isaac Newton, most likely, but also another guy named Henry Cavendish. He's born in France, but ended up working in England a little while later. Um, so go back to like 1687. We're talking about like 400 years, 300 or 400 years before this century. So this is a long time ago. And here's the genius of Sir Isaac Newton. He's following on the footsteps of Galileo, working with telescopes, things like that, just pittering around with natural philosophy. That's what they called physics a long time ago. And his genius was in not just that, like going, oh, things fall down, let me call that gravity. It wasn't just about the apple falling from the tree. But the genius of Sir Isaac Newton was in comparing that falling apple to the same reason that the moon hangs up there in the sky and never falls. There's not a very good connection there. There's not a big, obvious connection with that. But also, you might say Sir Isaac Newton was very into himself. You might say that because he said basically this. He figured that why is it just apples that are attracted to the earth? Why is the moon is attracted to the earth? Isn't everything in the universe also attracted to me? That's basically where Sir Isaac Newton's coming from. Because he hypothesized here and proved as well as he could that if you take any two masses in the universe, there's going to be a gravitational force of attraction between those two masses. Now, what he also hypothesized was the relationships, and figured out here that the relationship between two masses, 1 and a mass 2. Oh, let's switch over to my paper here. The relationship between these two masses produces a force between them. So that's the gravitational force. But he also conjectured that distance is a factor. Now I'm going to plug in the r squared. If you've done any work with the inverse square law, that's what this is. This is the inverse square law. R is a distance. So M is a M1 and M2. These are both masses. R is a radial distance. Radial is just a direction. So radial distance is a vector. It's a vector directed from the center of a circle outward from the radius. All right, so R is a radial distance. And with this, if you've heard of F equals ma, another one in Newton's work, it's Newton's second law, net force equals mass times acceleration. Force is a kilogram times a meter per second squared, and this is not kilograms meters per second squared. So Sir Isaac Newton figured there's got to be some kind of gravitation constant to make all this work. So G is called the gravitational constant. Gravitational constant. It's kind of like pi is a constant, but this is a physical constant. It's more like the density of water at standard temperature and pressure. Like at normal temperatures and air pressures and water pressures, what is the density of water? And that's what centimeter cubed and milliliter and centimeter, all those units of measurement are based off of. Grams, that's what those are all based off of. But this is a gravitational constant. It doesn't change. Problem is, Isaac Newton stopped there. He was not, he was a good scientist and he did a lot of excellent work. But there's a fellow who followed him named Henry Cavendish a little over 100 years later. So Isaac Newton did his work in 1687, and Henry Cavendish came along in 1798, of course a little bit before that, and he was actually able to measure and figure out what this constant was going to be. So that's over 100 years. Now, turn of the 1800s, we're still talking about not some pretty decent technology out there at the time, but we're still not quite getting up to trains yet. The locomotive. It's really approaching that time. So the locomotive hadn't even been invented yet. So there's a lot of technology yet to be done. So Cavendish's work was an experimentation. And here's the big problem that Sir Isaac Newton ran into. You see, he figured all this out. Like, it kind of makes sense, right? If you have a big mass and a small mass, you might get sort of a medium kind of force. If you get two big masses, you're going to get a huge force of attraction between them. Two masses that are small get a very small force. That's why if you and I were standing next to each other, we wouldn't be falling towards each other. But we do fall towards a really big thing that tends to be down all the time. That's the center of the Earth. So it takes a really large mass to make a significant weight force. And that's also what gravity can be called. It's a weight force. Now I got to be a little specific here. I did mention this was a vector, so there is a negative sign here to indicate that these two masses come together, they attract together. You might also say that weight is a vector, and I could write it like this. This is the magnitude of the gravitational force vector. It's just gm1 m2 over r squared. So I'm just looking at the amount of force for the rest of the time here. All right, so like I said, there's a problem with this if we're trying to solve for g. What is this constant? It needs to be experimentally determined. Well, if I've got, two masses that I can hold in my hand, let's say mass 1 and mass 2, all right, well, I can put them on a scale, right? Put them on a scale, and I'll make the scale go down, and I'll make this little meter go woo, kind of twist and turn, and kind of like a bathroom scale would. It would tell me, or tell Sir Isaac Newton at the time, how much this mass might weigh. Okay, so we can mass both of these masses. We can figure out their mass. All right, so check. We got those two masses. Can we measure the distance between them? Definitely. All right, we got an r. Now this would technically be the distance between their centers of mass. So we can measure r. Excellent. Now how about the force of gravity between them? Well, if you ever put a couple of balls on a table, they'll tend to roll off the table if the table's not level, or they'll just sit there if the table is level. There's not a large enough gravitational force to observe this Fg between mass 1 and mass 2. They're too attracted to their Earth to be able to be attracted to each other. Even just the tiniest bit of friction, the tiniest unsmoothness in the surface that they're sitting on, and these objects are not going to move towards each other. Now, if they're in the dead of space, totally at rest to begin with, eventually over time they will come together because there's no friction, no air resistance, anything to take away that energy. So the big problem is we don't know weight and we don't know big G. So if we don't know weight, we can't figure out that constant. All right, well, what else can we weigh? Let's back this up here. Let's try this experiment again. Okay, so if we're trying to find G again, what if we take a mass and we put it on the Earth? Okay, the Earth is a really big thing and it has a mass also. So we can measure wait a second, can we measure the mass of the Earth? We don't have the mass of the Earth. Oh, wait a second, let's see if we have anything else. Maybe this mass here that we're weighing, we could put it on we can put that on a balance, right? We'll put that on a balance, get its mass. Can we also put that object on a scale and get its weight? How much does it weigh? Yeah. Remember, mass and weight aren't the same thing. Weight is the force due to gravity, where mass is the amount of matter. Now, if you have more and more matter, you're going to have more and more weight. But if you go to the moon, your mass stays the same, but your weight will be decreased compared to the Earth if you're on the moon. So they are two different quantities. This is a force and this is an amount of matter. Can we possibly measure around Sir Isaac Newton's time the distance between an object on the Earth and the center of the Earth? Might be kind of hard, but actually they could have at the time. Definitely had the technology for a long time to be able to do that. And it's things called navigation instruments. They've been around the world a few times by the late 1600s. So definitely had a good idea of the circumference of a sphere, a spherical planet, and you can use that circumference with geometry to determine a radius of the planet. So yeah, we got an appropriate amount for the distance between a mass on the Earth and the center of the Earth. So again, we don't know the mass of the planet, and we can't therefore figure out G. So this has been the problem for Sir Isaac Newton. He was like almost there. It's like you know, trying to run a 10-mile race and you're at mile 9.5 and you just can't get that last half mile. So, what do? Well, wait a few hundred years, or at least about 100 years. Enter Henry Cavendish. He came up with this idea. How do I measure a minute force, a very small force of gravity between two masses? So he thought, what's easy to move, and can I get a force measurement from that? So he's thinking about like a cable or a string. If you ever take a lightweight string and you twist it, it doesn't take much force to twist. But when you twist it, what's it do when you let go? It tends to twist back. So he comes up with a good string, a good cable, and he does a few experiments. Now, if you go through my inertial balance lab, you'll probably remember that you can take some set mass measurements, put it on this moving tray, and measure the frequency, and use a graph to figure out how to compare frequency of motion to mass. In a similar kind of way, you could take a string attached to a bar, and you can twist that bar in a certain angle. And if you can measure the amount of force it takes to twist the bar, okay, we're going to measure that, and we're going to measure the angle at which you twist it, then you can get something like a force versus angle. Whoa, that's a funny little plot there. A force versus angle plot. All right. Now you might imagine the bigger the angle, the bigger the force. So is it a line? Is it a curve? It might be something like that. Whatever Cavendish came up with, he had something sort of like this, a force versus angle plot. Okay, so that's totally doable. Now, what do we do with the rest of the experiment? Well, we need a mass out here. And the thing with a mass out here is you're going to need something to balance it on the other side. So we're going to put an equal amount of mass on both sides of this bar. Okay. Next, we're going to pull up, once everything's at rest, we're going to pull up a couple of large masses that are on the floor, kind of on stands here. Mass 2 and another mass 2. These are my large bulbous masses. There we go. And you know what happened? This system, this bar, twisted ever so slightly. When those masses were brought close, it twisted. What about that? Okay, how about that? So when it twisted, he measured the R between them, got it equal. Okay, so we have an equal R. So look, he can measure the mass 1, measure mass 2. All right, measure the R. So we got mass 1, mass 2, and R. That's what Cavendish did. And wait a second, what about the force? Well, remember I said force is going to be related to the angle that it twists. So how does he get this ever so slight angle? It must be really hard to measure. So how do you increase angles? You can bounce a light off of a mirror. Okay, so he set up a mirror. It's a big old warehouse type of thing. And he shined, let me see if I can get a line here. Okay. He shined a light, shined a beam of light, called a laser beam type of thing. Okay. He shone it in, it bounced off the mirror. And when this thing twisted, it's going to deflect that reflected beam ever so slightly. And wherever it hits the wall, if we have a wall over here, I can measure this distance. And if you look at that, it makes sort of a right triangle. All right, so if we measure this distance and this little distance, we can use trigonometry, use a sine to figure out an angle. Sine of theta equals opposite over, maybe this is a tangent. Tangent of theta equals opposite over adjacent. All right, the side's very close to the hypotenuse. Could be either one. So with the angle, he can now measure the minute amount of force of attraction between the two masses. And guess what? Using a little algebra, bam, he solved for G. And G, this gravitation constant, is very close to 6.67 times 10 to the negative 11. Now that's the number. There's some excellent units. You can call it Newton meters squared per kilogram squared, and that'll give you newtons out of it. There's a couple other ways to write that. But as you notice, this is a very small number. For dose of perspective, this is 0.000, a whole bunch of zeros. 5, 6, 7, 8, 9, 10, and 11 would put it right there. So this is a very small number. Of course, there are some digits. The better the experiments, the closer we can get to it. And that will come years later. But he's able to measure this G value, or at least calculate the G value from other measured values. And you'll notice it would take a very, very large mass to make a significant force of gravity, because this gravitation constant is so small. All right, if you just measure even you and I, 260 kilogram people, I'm a little bit more than that. I'm just going with an average person here. If we have 260 kilogram people, we're still talking like 10 to the negative 7 newtons, or somewhere along that order of magnitude. Okay, it's just a very small amount of force. So that's a lot of sketching there. I hope you're able to follow that. So what can we do with this? Oh, well, what he did with it, he wasn't a very big person about it, but once all this word came out that he measured Newton's gravitation constant, he was able to calculate that from some accurate measurements. Guess what the newspaper headline was like? It must have been like this. It was like, "Scientists weigh the world." Scientists weigh the world. And you might be like, well, what do you mean? They didn't weigh it. They just found G, right? Well, if you know G, if you know this one, all right, and you kind of go back to our previous page here, remember when we were talking about different ways we can try to find G and none of them worked? We had to go to Cavendish's method. Well, you might remember that you can put a mass on a triple beam balance, and you can put that mass on a scale. So you can measure the mass of the object and the weight of the object. We can also know the approximate radius of the planet, okay? So this would be like the radius of Earth. Got that from, some navigational charts. So what's left? What can we find now that we know what G is? G, I'll write that again, 6.67 times 10 to the negative 11. Well, it doesn't take long for you to see that if you can measure the mass and weight of an object, you can calculate the mass of the Earth. Because in M1, M2, if you place some kind of M2 object on M1, which is the Earth, here it is, they're going to attract together with a gravitational force separated by a distance r. It's objects usually are at the radius of the Earth. So that M1 is the mass of the Earth, mass of our planet. And look carefully in here. The stats of the planet are involved in the force due to gravity. The only other mass involved is the object that's on the planet. So we could also write force due to gravity as mass times, we'll use a small constant, and this small little constant is 9.8 meters per second squared. Now that's specifically the force due to gravity between an object on the radius of the Earth, on the Earth's radius. If it goes up higher, like into space significantly, or if you're higher up on a mountain like Mount Everest, this R will increase and the weight will decrease slightly. So the Earth's, I believe the accelerations due to gravity on the Earth range between 9.78, like at the top of a tallest mountain, and about 9.81 at sea level. Okay, and we usually use about 9.8 because we're all most of us are slightly above sea level, except for the lucky ones that live along at the beach. I guess during hurricane season, they're not exactly loving it, but the rest of the time, we're all jealous of them, okay? So all of this is summed up as a little G character. You can write it, just simplify most things this way, and this is what we call weight. Weight is mass times 9.8 here on Earth, on the surface of the Earth. But all this helped us to mass the Earth. We weighed the world. But that's not all. Okay, this is one of those cheesy commercials. Gotcha. Okay, so I'm going to write this again just because I love it so much. m1, m2 over r squared. You see, for years, even before Sir Isaac Newton, think like biblical times, and even before, Babylon, okay? Babylon, I guess it might have been during biblical times here. The Babylon and into Persia, these were folks, and there were folks in the culture who were really smart, who looked at the stars all the time, and they used the stars to measure time, to keep track of time, and harvest. They keep track of the weather. When's the weather coming? When's the cold weather coming in? When's it going to heat up again? When does the rainy season tend to come? So this is big business. It's about keeping people alive. We're talking about some of the first large nations in the world trying to survive and stay dominant. So they put a lot of money into smart people keeping track of things. So for years, the Babylonians and the Persians later after them would keep track of the stars and where things are. And they would notice definitely that there are certain dots of light out there that moved throughout the season. Now, most stars just kind of stay in place. That's what we call the constellations. But the moving stars were planets like Mars and Jupiter and Saturn. It's a possibility that the wise men recorded in the Bible came from the Babylonian area, and they were looking at the stars and they saw maybe Jupiter. They called it considered that like the king of the planets. Was marching along, and maybe that had something to do with that bright star that they saw in the sky. But getting back to it, these Babylonians and Persians had all these star charts, and using this information and a couple other kind of star plotting techniques, so I don't have to go into it, we can get an approximate time period for planets to revolve around the sun. If you have a time period, add that to Johann Kepler's work. Here's another scientist. And guess what we could try to also figure out here? You see, if we know G, let's get a different color here. I'm changing colors all around. In this case, we know G already. And we now have, let's say, the mass of the Earth. If this is ME. Now, what does the Earth revolve around? What is it attracted to? The sun. So can we set this up with the Earth and the sun? Well, what about FG and R? Do we know the force of attraction between the Earth and the sun? Well, actually, yeah. It's not a direct method though. You see, the Earth is attracted to the sun and it moves in a circular path around the sun. And it doesn't fall towards the sun, so it is accelerating. It's getting faster? No, it's actually changing direction. You see, acceleration can be a change. Acceleration is a change in velocity, which could be a change in speed or a change in the direction of that motion. And when there's a change in direction, there's a little thing called centripetal acceleration, and with that, a centripetal force. So you see, through an indirect method, we can set this equal to the centripetal force of the Earth around the sun, which is related to an mv squared over r, okay? And the v is the motion of the Earth. And the motion of the Earth, along with r, comes from the period at which the Earth revolves around the sun. And we all know that time, right? How long does it take the Earth to revolve around the sun? About 365 days. So just without doing much more of the work than this, the time gives us the velocity worked in with the, oh, wait a second. What about the radius? Well, there's this thing called parallax, and anyway, we can figure out the radius, the approximate radius of the Earth revolving around the sun. There's a check mark. And if we know this radius and we know the time period that feeds in the velocity, the big point is we know indirectly the force due to gravity between the sun and the Earth. So guess what we can figure out now? The mass of the sun. Mind blown. We got the mass of the sun. Well, if we can figure out the orbital radius of Uranus, yes, we can figure out the mass of Uranus. So with the mass of the sun, if we plot where all the planets are in different parts of the year, we can figure out the mass of every single planet in our solar system. We could figure out the mass of the Earth. And we can figure out the mass of the moon that revolves around the Earth. And if we know the mass of the moon, guess what? With the mass of the moon and the orbital radius of the moon, we can determine the acceleration due to gravity on the moon. So there we have, go back, fast forward to 1960s into 70s, we have missions to the moon. We got the Apollo missions, and those smart folks at NASA figured out before they even got there what it's kind of going to be like when they're bouncing along on the moon's surface. That's right. They kind of know how much fuel they're going to need to give that lunar excursion module so that it can successfully land and then take off again and get back to Earth, bring all those astronauts back to Earth. So all this stuff stemmed from Sir Isaac Newton and Henry Cavendish finding that gravitation constant. So how do we use this? FG, I'm going to change back to something a little more visible here. Let's go with blue. Again, I can't get enough right in this. G m1 m2 divided by r squared. Okay. So what is if we've got two people, a mass 60, and their distance 2 meters apart, 60 kilograms. Whenever you plug in mass, it's in kilograms. So what would be the force due to gravity between two people? I mentioned that earlier. Let's see how close I was. G is 6.67 times 10 to the negative 11. It's always going to be that. Mass of one person, 60. Mass of the other person, 60 kilograms. Divided by the distance between them. That's 2 meters squared. Don't forget that square. All right, let's pull up the calculator. I've got 6.67. Now I'm going to use this calculator language using the E. So you can type in times 10 to the power of negative 11 as 3 different numbers with 2 different operations there, a multiplication and an exponent. Or you can make the calculator treat it as one, that little fat fingers there. Treat this as one single number, which tends to do a lot better. I'm just going to start over. One single number by pushing that second button. Let me bring up my full calculator. There it is. I'm going to cover me up. I'm not very important. 6.67, and I'm going to hit second, comma. Now my comma has that EE symbol on it. So if your calculator has that, try pressing that. It stands for a scientific notation exponent. So press that and then negative 11. And then we're going to multiply by 60 times 60. Okay, I'm done with that calculator for now. All right. Divided by r squared. So divided by 2 squared, or divided by 4. Now we get 6 times 10 to the negative 8 newtons. All right. Now Newton is a little less than 1/4 of a pound. Divide that by 4.445 newtons per pound. Then we get somewhere around a little less than 2 times 10 to the negative 8 pounds. Pen malfunction. Okay, that's not a lot of force. Just writing that out, that would be a 1,000th of a pound. But this is 4, 5, 6, 7, 8. So this is not a lot of force here. You don't feel each other as people are walking by each other. You're not falling towards one another. Okay, but I do have good news for you, everyone out there. Just know, positive thought of the day, that everyone in the world is attracted to you. Gravitationally, they are attracted to you. Unfortunately, they're not very attracted to you, but they are attracted to you. Positive thought of the day. All right, so one more application here. What if we go to Mars one day? What will gravity be like there? So let's try that out. 6.67 times 10 to the negative 11. Now I got to look up a little bit of information. If I'm 60 kilograms and I'm attracted to the surface of Mars, and I'm standing on the surface of Mars. I'm going to look up in a table, got an excellent university physics by Young and Friedman. This is 15th edition, and right in the back, there's a wonderful chart, okay? Wonderful chart that gives us a bunch of information about Sun, the Moon, Mercury, Venus, Earth, Mars. There it is. Mars has a mass of 6.42 times 10 to the 23. Did they put that thing on a scale? No, they used Newton's universal law of gravitation and Cavendish's constant. Okay, so Mars has a, now you know that where that stuff comes from, okay? It has a mass of 6.42 times 10 to the 23rd kilograms. And we're going to divide that by the radius of Mars. Okay, that's my person there. Okay. That's how much I'm attracted to you all. And I'm 2 meters away. Okay, anyway. Mars has a radius of 3.39 times 10 to the 6 meters. 3.39 times 10 to the 6. That's 3,390 kilometers. So is that it? No, don't forget to square that. Don't forget to square that. There it is. Put the book away. So now we're ready to calculate this here. So 6.67 e negative 11 times 60 times 6.42 e 23. Now if you're using the e's, you can just do divided by 3.39 times 10 to the 6th power. If you use the e, you can just put squared. If you use times 10 to the power of, you better put that in parentheses. All right, if you want to square that. But on my calculator, this will square that whole 3.39 E6 number. Won't treat it separate. And look at that, I get 223, around 224 newtons. Now on Earth, 60 times 9.8, this person would weigh 60 times 9.8, 588 newtons. You see, if we go to Mars, we're going to weigh less. All right, how about that for a weight loss program? You can lose more than half your weight in 6 months or so, however long it takes to go to Mars. Okay, so 224 newtons. Well, what would G then be? What would acceleration due to gravity on Mars be? Well, that would be 60 times some little g for Mars. But I've got the force due to gravity now. I can plug that in. 224 equals 60 times g for Mars, divide by 60. So if you take the weight divided by your mass, to just divide that out again, then you get a g for Mars of, well, let's see, 224 divided by 60. 3.73 meters per second squared. On Earth, it's 9.8 meters per second squared. There. All right, so just a little over a third of our weight if we go to Mars. So that's just a few applications of using Newton's universal law of gravitation. The applications of using the universal law are universal. I'll leave you with that.